Hello and welcome to another stats review video. All right, so let's see what we have here. A student is chosen at random from the River City High School student body, and the following events are recorded. The student is male, the student is female, the student ate breakfast, the student did not eat breakfast. The following tree diagram gives the probabilities associated with these events. Given that a student who didn't eat breakfast is selected, what is the probability that she is female? All right, so this is basically saying what is the probability of being female given that you had no breakfast? I'm just going to use the N there for no breakfast. All right, now this involves using the conditional probability formula, which states that the given becomes the bottom of your fraction. So the probability of no breakfast over the probability of these two pieces ANDed together. So the probability of being a female and having no breakfast. All right. So we can use the chart to figure out these various things. So if there's a 40% chance of being a male and males eat breakfast 80% of the time, then that means 32% of our population are males that eat breakfast. Right? By that same logic, 8% of our population is males that don't eat breakfast. Right? And again, I'm just multiplying these numbers together, but notice they add up to the 40% that comprise the males. Females are 60%, 30% which eat breakfast. So that brings us to 18% of the total population are females that eat breakfast. And then 0.6 times 0.7 is 42% of the total population are females that don't eat breakfast. So now that we have this, we can find out the combined probability of those that don't eat breakfast. Right? It would be this one right here and this one right here. So when we're filling in our formula here, the bottom of our fraction is going to be 0.42 plus 0.08. And then the top of our fraction is females that don't eat breakfast, which is this branch right here, or put another way, 0.42. And then at this point, it's just putting that into your calculator and kind of seeing what you get. So 0.42 divided by 0.5, that's going to give us 0.5 there, is going to be 0.84, which I'm fine with as an answer, but you could also write it as 84%. All right, but basically knowing how to read one of these charts, knowing the conditional probability formula, and being able to plug things in and kind of figure that out. 2, the following table compares the gender of 200 Canadian high school students and what methods they prefer using to communicate with their friends. Show a calculation to support that the event male and the event in person are not independent. All right, so we're saying not independent. Now to compare this, we have two options. We can compare the probability of being male with the probability of being male given that you prefer in-person communication. Or we can compare the probability of in-person to the probability of in-person given that you're male. Now, not independent means that these should be not equal to one another, right? If it was independent, we would expect these to be equal. We would expect these to be equal. But since we're trying to show that they're not independent, we're expecting them to be not equal to one another. Now, probability of being male, there are 34 males in total out of 200, which works out to be 17%. And what we're hoping that whatever this is not 17%. So the probability of being male, given that you're in person, would be this column right here, or 12 out of 85. And 12 out of 85 is more like 14%, so 0.1412. So that shows us that they are not independent. Now, I could also perform this calculation. It's going to reach the same conclusion. So in person is 85 out of 200, or 0.425 as a percent. And then the probability of in person, given that you're male, would be using this row. And that would be 12 out of 34. And 12 out of 34 is 0.3529. So it doesn't matter which one you do. They're reaching the same conclusion. All right. They are not independent because these two probabilities are not the same. Or if you did this one, these two probabilities are not the same. If these had been equal, we would have said it was independent. If these had been equal, we would have said it was independent. But in this case, we're saying that it's not independent. All right. An SRS of 100 workers found that the average time they spent with their first employer was 6 years, with a standard deviation of 2 years. Assuming the distribution for this is approximately normal, a 95% confidence interval for the mean time the population of workers spent at their first employer is what? All right. So again, that's going to bring us to our calculator. All right. We're down in the interval section. And then it's a question of which one are we using? All right. So we only have data on one group. So that rules out any of the two choices. All right. This is not a proportion. We're not dealing with like a proportion of successes here. So that rules out that. That leaves Z and T. And hopefully you remember that I said we never use Z interval. All right. That would be if we know the population standard deviation, and we don't know that. So that means we're using T interval. All right. If I go to T interval, you're going to see I have a choice between data or stats. Data or stats. I'm going to use the stats option here because I don't have any data. All right. It tells us that the sample result was 6. So my X bar is going to go in as 6. It told us the sample standard deviation was 2 years. So I'll put that in as my S of X. And it told us that our sample size was 100. So that'll go in as my N. And then the confidence level is 0.95. All right. So once I have all of that in there, I can hit calculate, and it'll generate my interval, which is 5.6032 to 6.3968. All right. So that's basically saying, all right, we're 95% confident the true average time is somewhere between like 5.6 and 6.4 years. Right? But again, knowing how to look at a problem and then being able to go to this menu and understand which one you have to use to get the correct result. All right, number 4, according to the Humane Society data, 39% of households in the US have at least one cat. In the UK, 23% of households have at least one cat. Suppose you select an SRS of 75 households in the US and 80 households in the UK, and you calculate proportions for both of those, P1 and P2. What is the mean and standard deviation for P1 minus P2? So if we subtract these two samples, what is our new mean? What is our new standard deviation? So the new mean of P1 minus P2 is just going to be those percentages we calculated subtracted from one another. So if we're doing P1 was US, so it's just 0.39 minus 0.23 for a 0.16. All right, this is the distribution of the differences between these things. You know, this is what we do for like a 2-prop Z interval, all right, a 2-proportion confidence interval. Now, the standard deviation of P1 minus P2 is, remember, when we're combining standard deviations, it doesn't matter whether we're adding or subtracting, we still add the variances. Now, for any one of those, the formula is this, right? This is your standard deviation formula, which means the variance is just that without the square root, because the variance is just the standard deviation squared. So we're going to take the variances, P1, Q1 over N1, plus P2, Q2 over N2. That would be the variances. We're combining the variances, and then we're going to take the square root to turn that back into a standard deviation. All right. So same thing that we've done before, combining random variables. It's a little uglier with all the percentages and decimals here. So this works out to be, let's see, 0.39 times 0.61. And then for the US, our sample size was 75 plus 0.23 times 0.77. And then for the UK, the sample size was 80. All right. And then once you've got that set up, then it's just a matter of typing it into your calculator and working it out. So 0.39 times 0.61 divided by 75 plus 0.23 times 0.77 divided by 80. And then I have to take the square root of that. And I end up with 0.0734, we'll say. So those are my two answers. This is my new mean. This is my new standard deviation. All right. But again, it's that idea of combining random variables. You just add or subtract the means. But when it comes to standard deviations, you have to add the variances and then take the square root to turn it back into a standard deviation. Number 5, an SRS of 100 train arrivals by Amtrak showed that 60 were on time. An SRS of 100 flights by Delta Airlines showed that 83 were on time. Let PA be the proportion of on-time train arrivals, and let PD be the proportion of all on-time flights for Delta. A 95% confidence interval for the difference between PA and PD is what? All right, so again, we're going back to our menu. Stat tests, we're looking for an interval here. All right. Now, Z and T deal with means. All right. We're not dealing with means here. We're dealing with proportions. So that brings us down to A and B. And this time we have two data sets. We've got information about Amtrak and we have information about Delta. So that's going to bring us down to the 2-prop Z interval. All right. Now, the calculator does x1 minus x2. So the problem is telling us Amtrak minus Delta. So we have to make sure that we put the Amtrak information in first. So Amtrak had 60 on time out of a total of 100. And then Delta had 83 on time out of a total of 100. And we're doing a confidence level of 95%. All right, so once that's all in there, let's see. 60, 100, 83, 100 again. Okay, 95%. We're going to get that result right there, all right, which is 0.351 or a negative 0.351. 0.351 to negative 0.109. All right. Now remember, this is an interval for the differences. So this is basically saying, because we're doing Amtrak minus Delta, Amtrak has somewhere between 35.1% and 10.9% less on-time arrivals. All right, because to get negatives, that means the Amtrak value is lower than the delta value. And lower in this case is bad because we're talking about on-time arrivals. So they've got somewhere between 35 and 10% more late arrivals or less on-time arrivals. Number 6, but again, really this is about going to that menu, being able to figure out which one you need, and then provide the correct information to get the answer. And again, with these 2 ones, it's important that you type them in the right order. Otherwise, it'll kind of flip the signs on these. And if it was like a multiple choice, you're probably going to see one that's negative and one that's positive. So you have to make sure that you're putting them in the right order. All right, number 6. Random samples of male and female high school students were asked to identify their favorite food group. Here are the results. All right, so carbs, dairy, fruits and vegetable proteins, and then gender, male, female. Expected counts for each cell were given in the following table. So this is what was expected to happen. What is the individual component of the chi-square contributed by the cell, male, and proteins? So to do this, you kind of have to just know what's the formula for calculating a chi-squared statistic. And generally, it is the observed minus the expected squared divided by the expected. All right, because chi-squareds can only be positive. They can never be negative, and the squaring takes care of that for us. So let's see, we're doing male proteins. So that would be this one right here and this one right here. So we observed a 17. We were expecting a 10.2. We're going to square that, and then we're going to divide it by 10.2 because that was our expected value. All right, when we do that, 17 minus 10.2, square that, divide by our expected, we end up with 4.53. So that would be the individual component of our chi-squared statistic contributed by males and protein. All right. So hopefully this was useful. Again, chi-squared, how to calculate that statistic, going through the menu, choosing the appropriate choice, combining random variables, again, using the menu, how to test for independence, and then the conditional probability formula. All things that you should be aware of and have some degree of comfort with heading into the final. Okay? So as always, let me know if you have any questions, and best of luck. All right, bye.